Day 37, Honors Physics, problem number 31, Newton's 3 laws. A couple of things going on here. First of all, watch out for the units. They give you the masses in grams. We would like kilograms. And like a lot of problems, there's alternate ways to do this one. This is one of the easier ways. If you look first at the bottom mass, and you solely draw the free body diagram for that mass, well, it's got a weight of 12 newtons. Now there is no support or normal force on this mass. I was ready to draw that, but it's not sitting on a floor, so it's not supported by something underneath it, but it's being held up or at least pulled on by the string or the rope, which has a tension in the upward direction. Now I actually know that that tension, I'm going to call it T, that represents how tight that rope is between the two masses. And right now I'm concentrating on this lower mass, but that tension has to be less than 12 newtons because the whole system, including that mass, is accelerating down. If I apply F net equals ma to this mass or this free body diagram, because those are the only two forces acting on that bottom mass, that's F net equals ma. So F net now with two forces, you take the big force minus the small force. The bigger force has to be down because it's accelerating down. So it's 12 minus T equals 1.2 times 4, because it tells me the acceleration is 4. So therefore you can get T. That's the tension in that rope between the two masses. So that's part of the problem. But we also need the tension in the rope at the top. There's two ways to do this. I'm going to sort of do it the longer way, but you could, I'll tell you the shorter way as well once I finish the longer way. So if we call that part A, they really don't delineate part A and part B, but part B now is going to be the tension in that top rope. If I do the same thing I did in part A, if I look at the top mass, all right, it has a mass of 0.8 kilograms, so it weighs 8 newtons, but it has a rope at the bottom pulling down on it. Well, that rope on the bottom pulling down will have a tension, T, that's the same as the answer for part A, because that's the rope between them, that's how tight it is. So that would be a known number. That's the answer you had from part A, so that would be your T. I'm going to call that T sub 1. Let me put that all in here. That's T1, lower rope, T sub 1. Because there's a second rope which could have a different, well, probably will have a different tension, the rope at the top pulling up. I'm going to call that T sub 2. How tight the top rope is, that's T sub 2. So for that upper mass now, there are three forces that would contribute to the net force. And if we plug into F net equals ma for that upper mass, it's going to be the bigger force minus the smaller force. Well, the bigger force is going to actually be the sum of the 8 plus the T1. So you're going to have 8 plus T sub 1 is the downward net force minus the upward force T sub 2. Once again, I know T sub 1 equals m, which is 0.8 times a, which is 4. So the only thing I don't know is T sub 2. You can solve for T sub 2. And that's the final thing you need here. Now, another way you could have done this problem, I'm not going to do it this way, is you could have lumped these two together, kind of like we did with the train problem. In other words, take the 1,200 grams plus the 800 grams gives you 2,000 grams or 2 kilograms, and make that one big mass. And then it kind of takes out that middle piece, that middle rope. So all you would have is a 2 kilogram mass with a tension upward, which is T2. And you just have an F net equals ma, and the only F net would be T2 on that big mass of 2 kilograms with an acceleration of 4. Don't need to do it that way, but that would have been a little bit faster way to do part B. And part A, actually. Well, part B, you wouldn't be able to do part A that way because you need to separate the two masses to get part A.